Okay, it's 2 p.m. So if you could please type here into the chat window to let me know that you're present. Thank you all. So what we are going to be doing today is kicking off a series of several lectures related to steady state sinusoidal circuit analysis. So in very broad terms, steady state sinusoidal circuit analysis is the analysis method that's used to analyze the power systems in the industrialized world. Electricity is transmitted over long distances from distribution centers or power plants to businesses and homes using sinusoidal waveforms. Here in the United States, those sinusoidal waveforms are oscillating at a frequency of 60 hertz or 60 cycles per second. And in most of Europe, electricity is distributed at an operating frequency of 50 hertz or 50 cycles per second. So before we get too in the weeds with our analysis of these systems, we need to review two very specific topics. And we're going to cover both of them today. So the first topic that we are going to talk about is complex numbers. So what I'm going to put here kind of in the middle of the page is a complex plane where our vertical axis will correspond to imaginary numbers and our horizontal axis will correspond to real numbers. Okay. So effectively, the real number axis is just the number line that we learned about in elementary school, or at least I learned about in elementary school. And then perpendicular to that real number line is an imaginary number line, okay? And so a complex number is simply a number that contains both real and imaginary components. So the first way that we'll learn to express complex numbers is in a rectangular format. And I'm going to say that a complex number A, in a textbook, you might see a complex number A written as A in boldface, but because I can't write in bold, I put a bar over the top to indicate that we have a complex number. And I might say that this is lowercase a plus JB. Okay. We're going to talk about all of the different parts of this guy. Okay. So the real part of complex number A is lowercase a, and the imaginary part of complex number A is lowercase b. How we might graph such a complex number would be something like this. So we would go out A units in the real direction. We'd go up because we have plus JB, B units in the imaginary direction, and then our complex number would be a two-dimensional vector that's A units in the real direction and B units in the imaginary direction. So it's a combination of real and imaginary parts. Okay, Our complex number plane is nothing more than a 2D Cartesian coordinate system like we are all used to. Okay. All right, so we can also represent complex numbers in an exponential format as well as a polar format. Okay. The exponential format for a complex number and the polar format for a complex number contain the exact same information. The polar notation is just a shorthand notation for the exponential. So our two-dimensional vector here has some length. We're going to call this the magnitude of A, and it forms some angle, theta A, with the real axis. So our exponential form of complex number A is simply the magnitude of A, e to the j theta A. And our polar form, sorry, let me erase that bar there, is the magnitude of A angle theta A. So the polar form, again, is nothing more than a shorthand notation for the exponential system. Okay. They have the exact same pieces of information. They are 100% interchangeable. Now, we all use calculators in this class, okay? And our calculators are capable of doing mathematical manipulation of complex numbers, but we have to be careful about it, okay? So the first thing that I want to note is that your calculator will only accept complex numbers in polar form and rectangular form. You cannot enter a complex number in your calculators, or at least the calculators that are approved for use in this class, in exponential form. It does not understand that, okay? Now, another thing that we have to be careful about, and I'll do this in a different color, is this J, because your calculators do not have a J button, okay? So let's talk about the concept of J. In your earlier classes, you likely learned that I, the imaginary operator, was equal to the square root of -1. Well, in electrical engineering, I is used to reference currents. So that would be unnecessarily confusing. Instead, we've simply incremented the alphabet by one letter. And so electrical engineers use the letter J to represent the imaginary operator, the square root of -1. Okay. So while we're on the topic of the imaginary operator J, I want to develop a simple table here that will be of use to you all, because some of your calculators are incapable of expressing J beyond a certain range, okay? So I'm going to start here in the middle with J to the 1, which is simply J, and that is equal to the square root of -1. J squared is then the square root of -1 squared, which is -1. J to the 3rd power is just J times J squared, which is -J. j to the fourth power is just j squared times j squared, which is positive 1. And then j to the fifth power is just j to the fourth times j, which is just j. And then that cycle repeats itself. We go in the other direction. J to the 0 must be 1 because anything raised to the 0th power is 1. J to the negative 1 is 1 over the square root of negative 1. And if we multiply this by the square root of negative 1 over the square root of negative 1, this becomes negative j. J to the minus 2 is just 1 over j squared, which is negative 1. And j to the minus 3 is, let's see, 1 over j squared times 1 over j. So that's negative 1 times 1 over j gives us positive j. And again, we see that it just cycles over and over and over again, right? So it goes j negative 1, negative j 1, j negative 1, j positive, or negative j positive 1. Just cycles those four values over and over and over and over again. So if you have a if you have a Casio FX991, you can put in j to any power that you want and your calculator can easily process it. If you have a TI-36X, I believe you can put in j to any power that you want and your calculator will process it. But some of you guys use Casio 115s. That's probably the second most common calculator I see for Circuits 1 students to use. And if you put in j to anything above the third power or anything more negative than the negative third power, your calculator can't process it. So what you would do is simply subtract 4 from positive exponents until it falls into the correct range, or add 4 to negative exponents until it falls into the correct range, and then you'll get the result that you want. So j to the 7th is the same thing as j to the 3rd, and then your calculator could do it. J to the negative 10th is the same thing as j to the minus 2, and then your calculator could do it, okay? So we have to be careful about our imaginary operator and powers associated with that imaginary operator for some of the calculators that are approved for use in this class. All right, so we have introduced the rectangular form for complex numbers, the exponential form for complex numbers, and the polar form for complex numbers. Now it might be useful to explain how to go back and forth between these relationships. And it's just simple trigonometry. So for example, let's talk about how we could express the exponential or polar form in terms of the rectangular portions, right? So the magnitude of the complex number a, and this is true for both the polar and exponential form, is simply the square root of the real part of the complex number squared plus the imaginary part of the complex number squared. And this is purely from the Pythagorean theorem. We have a little right triangle here that's a units of base, b units of height, and the length of the hypotenuse has to be the square root of the base squared plus the height squared, okay? Nothing remotely difficult there. Our angle, theta A, we can express in numerous different ways. But the easiest way, in my opinion, is the inverse tangent or the arctangent of the imaginary part B over the real part A. So this is how we determine the magnitude of our complex number and the angle of our complex number in exponential and polar format from the rectangular coordinates. We can go the other way around and say that A, the real part of complex number capital A, is simply the magnitude of A cosine theta A, and B will be the magnitude of A sine theta A. So these are our relationships for swapping back and forth. Now, we have to be very careful about doing these calculations by hand. In fact, this is one of the few instances where I would encourage you all to always do this manipulation using a calculator and to pretty much never do it by hand. And I'm going to illustrate why with a quick example here. Okay. So let's say that we have a complex number B. And B is equal to -3 plus J4. And we want to find what the polar form representation of this complex number B is. So the magnitude of B would be equal to the square root of -3 squared plus 4 squared, which is the square root of 25. So our magnitude is simply 5. Our angle, theta B, is given by the inverse tangent of the imaginary part, which is 4, divided by the real part, which is -3. And if I throw this into a calculator, give me just a moment to do this. I get -53.130 degrees. Putting these results together, we would assume then, sorry, it should not have the magnitude sign on the outside, that the polar form representation of B is equal to -3 plus J4 would be 5 angle -53.130 degrees. This is actually not true. If we plotted our number on the complex plane, where this is the real axis and this is the imaginary axis, we would go back 3 units, up 4 units. So this is what B should be, right? So this is -3 units in the real direction, and this is +4 units in the imaginary direction. According to our polar form representation, we should have a length of 5 units with an angle of -53.130 degrees. So the problem here is that our calculator can't tell the difference between actually, let me do it this way. So the inverse tangent of 4 over -3 is the exact same thing as the inverse tangent of -4 over +3, which makes sense, but our angle winds up in the wrong quadrant because the arctangent operation will always return an angle that is between +90 degrees and -90 degrees, okay? So if we're doing this calculation by hand, we have to be extra careful. But our calculators are smart enough to where if we put in the complex number -3 plus J4, and we tell the calculator to give us the result of that in polar form, it will not make the mistake that I've illustrated here. It will give us an answer of +5. Let me throw it in here real quick. So if I type in -3 plus 4i on my calculator, and then I tell it to give me my answer in polar form, I get 5 angle 126.869 or 870 degrees, which is what this angle right here actually is, okay? So it is critically important for your success in this third section of our class that you learn how to use your calculator to input complex numbers in one form and have it give them back in the other form, okay? Normally, I would literally walk around the classroom showing people how to use their calculators, but I can't really do that with this online modality. So after I finish lecturing today, if anybody has any questions about how to do that with their calculator, I'm happy to hang around and at least talk you through it, because I have in my office right now a Casio FX991, a Casio FX115, and a TI-36X, which are the 3 most commonly used calculators that students use in this class. Every now and then a student will use a HP calculator. I honestly have never in my life used one of those. So I don't know how to help you there. You'll have to use YouTube and Google and all that kind of stuff to figure it out. And if you have a TI-30, I would highly suggest that you upgrade to a more powerful calculator, because you're going to spend a lot of time doing ugly manipulations that a calculator that's literally $5 more expensive can do for you. So anyway. All right, so let's talk about mathematical operations for complex numbers. And actually, before we, the first operation that we're going to talk about here is going to be the complex conjugate operation, and it's going to require us to use a complex number plane to understand it. So let's do that one on this page before we move to the next, okay? The conjugate operation is as follows, okay? If we have a complex number, A, I apologize again, I keep wanting to put the magnitude signs around it, but if I have a complex number A is equal to A plus JB, the conjugate of A, denoted by this asterisk to the right of the complex number, is simply A minus JB. So the conjugate operation changes the sign on the imaginary part of the complex number. So on our representation of A on our complex plane, we would simply go down negative B units instead of positive B units, and we would wind up getting this number, which I'll designate as A conjugate. Well, over here in the exponential and polar form regime, the conjugate operation does the exact same thing. So effectively, instead of having this angle theta A, we now have an angle of negative theta A. So the conjugate operation acts on an exponential or polar form complex number by changing the sign of the angle. So our complex number, I did it again, my apologies. Our complex number A is of the form A e to the j theta A. Then A conjugate would be the magnitude of A e to the negative j theta A. And if we have a polar form complex number where A is equal to the magnitude of A angle theta A, then the conjugate of A is simply A angle negative theta A. Okay, so that's the conjugate operation. Again, nothing more than changing the sign on the imaginary part, which winds up flipping the sign on the bit in front of J, or flipping the sign on the angle in our exponential and polar representations. Now let's go to the next page here and get into more normal, I'll call it, mathematical operations that you're familiar with. So the first operation that we are going to look at is just good old addition. So let's say that I have a complex number A, which is equal to A plus JB. And I have a complex number B that is equal to C plus JD. If I want to perform the operation of A plus B, what I will get is A plus JB plus C plus JD, or A plus C plus J, E plus D. So addition works just like adding together two-dimensional vectors did in your physics class. We add the real components together, we add the imaginary components together, and we form our resultant 2D vector, okay? So addition is pretty straightforward. Now we'll talk about subtraction. Also going to be pretty straightforward. For complex number A is equal to A plus JB. Complex number B is equal to C plus JD. Then A minus B is going to look like A plus JB minus C plus JD. So we'll have A minus C plus J, B minus D. Again, this is nothing more than how we would subtract two-dimensional vectors from each other in our physics classes. We can do it graphically using the tip to tail method as well if we need to, but I don't think we'll ever really have to do that in this class. All right, now let's talk about multiplication. Here's where things are going to get a little bit more difficult. So again, let's say that A is equal to A plus JB, and B is equal to C plus JD. From here, multiplying A times B will look like this. And I want to point something out. If you see two complex numbers next to each other, that means that multiplication is happening. I'm going to write some things down here just to explicitly say you will never see me do this, okay? I will never write A times B like this because it could be confused as a cross product operation, because we would, that to me looks like vector A crossed into vector B, and cross product operation does not exist for complex numbers. So you will never see me write the multiplication of complex numbers like that. Similarly, you will never see me write the multiplication of complex numbers as A and then using effectively a dot operator to indicate multiplication. Dot products don't exist for complex numbers either. So I don't want to confuse those of you who are familiar with vector calculus with a cross sign for multiplication, because I don't want you to think you need to do the cross product operation. I will never put a dot in the middle because I don't want you to think that you should do a dot product operation. Another thing that you may see would something like A and then asterisk B. Well, that would be too confusing with our conjugate operation, okay? So if you ever see, so all of these are very, very bad and I will not use them. If you ever see something like A asterisk B, that means I am asking you to multiply the complex conjugate of A times B, okay? So a little bit of a rant there, but I wanted to be very, very clear about the notation that will be used to avoid further confusion, okay? So if I'm multiplying A times B, this is going to look like A plus JB times C plus JD. And now I'm going to just simply FOIL this out. So I'm going to have A times C plus J, A times D, plus J, B times C, plus J squared, B times D. Now, if we scroll up here and we look at our table, J squared is actually just -1. So from that, we could write this as AC minus BD plus J AD plus BC. That would be the result of the multiplication operation acting on rectangular form complex numbers. Now, let's talk about division. So for complex number A is equal to A plus JB, and complex number B is equal to C plus JD, division A over B, and I'm giving myself some room here because I'll explain it in a second, would look like A plus JB over C plus JD. And it appears that we can't actually do any simplification here. what we are going to do, okay, so let me explain what's happening here. So when we added two rectangular form complex numbers together, the result of that operation was a rectangular form complex number. When we subtracted two rectangular form complex numbers, we got back a rectangular form complex number. We had a real part and an imaginary part. When we multiplied two rectangular form complex numbers, we got back a rectangular form complex number. So I am expecting for us to get back a rectangular form complex number, and we're not getting that right now. We're getting a ratio of rectangular form complex numbers, which is not the same thing. So how we're going to rectify this is we are actually going to multiply our division, and I don't want to put that X there, by B conjugate over B conjugate. So I'm going to multiply that fraction by another fraction. Our fraction B conjugate here will look like C minus JD over C minus JD. And so what's going to happen is, let's FOIL out the numerator. We're going to have A C minus J A D plus J B C minus J squared B D divided by C squared minus J C D plus J C D minus J squared D squared. So minus JCD and plus JCD cancel each other out. This term right here of minus J squared looks like plus 1. This term up here of plus J squared also looks like plus 1. And so what we get, and I'm running out of room here, bear with me, is going to be AC plus BD over C squared plus D squared plus J BC minus AD over C squared plus D squared, so that we now have a rectangular form complex number with a well-defined real part and a well-defined imaginary part. Okay, so multiplication using rectangular form complex numbers is tedious but straightforward. Division of rectangular form complex numbers can be a bit of a pain in the butt. So instead, what we're going to do for both multiplication and division is look at what happens with with exponential form complex numbers, and then apply that to polar form complex numbers as well. So over here on the right, let's say that we have a exponential form complex number, the magnitude of A, e to the j theta A, and complex number B is equal to the magnitude of B, e to the j theta B. Then multiplying A times B looks like the magnitude of A, e to the j theta A times the magnitude of B, e to the j theta B, or the magnitude of A multiplied by the magnitude of B times e to the j theta A plus theta B. So multiplication using exponential forms, you simply multiply the magnitudes and add the angles and you're done. Much easier. In polar form, this would be magnitude of A, magnitude of B, angle theta A plus theta B. So the exact same thing. Multiply the magnitudes, add the angles, and you have your resultant complex number. Now let's look at division. For complex number A is equal to the magnitude of A e to the j theta A, and complex number B is equal to the magnitude of B e to the j theta B. Division is going to look like the magnitude of A e to the j theta A over the magnitude of B e to the j theta B, which in turn just looks like the magnitude of A over the magnitude of B e to the j theta A minus theta B. And in polar form, this is simply the magnitude of A over the magnitude of B, angle theta A minus theta B. All right, so it is my expectation that you guys learn how to perform all of the mathematical operations that we've detailed today using your calculators. Okay? I honestly do not expect you to be able to do any of this by hand. It's not a bad idea to know how to do it, and I will use some of these relationships that we've developed today to explain some things later on in the class. But as far as number crunching and things like that goes for your homework assignments and your exams, your calculator is a very, very powerful tool. I do want to point out that your calculator does not care whether or not you use all rectangular complex numbers, all polar form complex numbers, or some combination of both. It is capable of performing the math correctly, regardless of what you input. Your answer will come out in the form that your calculator is set to. So there's a setting in your calculator, if you go into the setup function, where you can choose what type of complex number result you get, either polar form or rectangular form. Use whichever one you're comfortable with, and then there is a conversion button on your calculator, usually hidden inside of a menu, that will let you convert from rectangular form to polar form and from polar form to rectangular form. So effectively, you can just set your calculator in whatever mode you're most comfortable getting the result in, and then you can get the other form just doing a very quick conversion. All right, so that is what I wanted to talk about regarding complex numbers. Before we move along to our second half of this lecture, does anybody have any questions or comments or concerns? All right. So what we are going to talk about now is another review section here, where we're going to talk about sinusoidal signals. And here, we're laying the groundwork for our analysis. All right, so I want us to consider a sinusoidal signal, and I will do my best to draw this as least crappily as possible but please bear with me. So in this case, my sinusoidal signal, and I'm just going to call it x of t, will be a function of variable t indicating time. And my waveform will look something like this. All right, so I have attempted to draw a sinusoid here. My apologies for its lack of symmetry and things. I'm honestly trying my best. So x of t can be expressed mathematically as x sub m cosine omega t plus some phase angle, which I'm going to call theta, or it can be expressed mathematically as x sub m sine omega t plus some phase angle that I'm going to call phi. Now, for reasons that I am not yet ready to discuss with you guys, we will 99.9% of the time deal with sinusoidal signals expressed as a cosine function. This cosine function representation is going to be what we consider our baseline for all sinusoidal signals. In fact, in a little bit after I introduce some trig identities, we will easily be able to convert a sine representation into a cosine function, which is going to be required of us fairly regularly. Okay. So now I want to talk about the different constituent parts of this mathematical representation. Okay. So let's start with that bit x sub m. So what x sub m represents is the distance from the horizontal axis to the peak value of the sinusoid. It does not matter if it's a positive peak value or a negative peak value. Xm should be exactly the same. Okay, so x sub m is the amplitude. You may hear this or hear me call this magnitude as well. Of the sinusoidal function. And it represents the maximum value. Okay. Now let's talk about omega. But before we can talk about omega, we need to actually represent something else. Okay. So the distance from the negative peak value to the negative peak value is what I'm going to call capital T. and it represents the period of the waveform. We could also represent the period as the distance between positive peaks. We could also represent it as the distance between increasing zero crossings or decreasing zero crossings, but I don't want to get too wild or crazy with you guys. So we'll just deal with the peak value representation of the period, okay? So T is the period of the sinusoidal wave function, and it represents how long it takes for measured in time for one cycle of the sinusoid to occur. F is the linear frequency of the sinusoid, and mathematically F is equal to 1 over the period, okay? So if T is the period of the sinusoidal function, or how long it takes one cycle to occur, measured in seconds, then F is a measure of how many cycles per second occur. Omega is the angular frequency of the sinusoid, where omega is equal to 2 pi f, or 2 pi over t, okay? So I'm going to go back through here and we're going to talk about units, because the units here are very, very important, okay? The unit of the period is usually seconds, okay? It might be milliseconds or microseconds or nanoseconds or something like that, but the period is a measure of how long it takes for something to occur. So it is an indication of time, and traditionally that is measured in seconds. Linear frequency F then has units of per second. Let me make this more obvious that that's seconds to the -1 power. And this is commonly referred to as the unit of hertz, where 1 hertz corresponds to 1 cycle per second. Our angular frequency, omega, is the total angle traveled in a specific amount of time. And so this has units of radians per second. So omega is equal to 2 pi f, because in a single cycle, the angle changes by 2 pi radians, or it makes a full circle, okay? All right. Our last thing that we're going to talk about is our phase angles. I'm only going to talk about theta. Phi is just also a phase angle, but with a sinusoid as a baseline, okay? So theta here is the phase angle of the sinusoid. What it represents is how much our sinusoid is shifted in time. So let me explain exactly what I mean by that. Okay. So if we look at this sinusoid I've drawn here in red as a cosine function, we would expect that its maximum value would occur at lowercase t is equal to 0. Okay, because the maximum value of a cosine function by itself is +1, and the cosine of 0 degrees or radians is equal to +1. Instead, the peak value of our sinusoidal function has been shifted to the right by some amount, which I'm going to call delta t. Okay. Well, this value delta t is directly related to the phase angle and the angular frequency. Okay. So in general, the magnitude of the phase angle is equal to omega times delta t. But I'm going to give us some special rules here, okay? So if the sinusoid is shifted to the right, so what this means is that the peak value occurs at a later point in time than it would with a phase angle of 0, then theta is negative. Conversely, if the sinusoid is shifted to the left, then theta is positive. This may seem awkward to you all. In fact, I get asked a lot of questions about this very regularly, including, are you sure you have the sign rights or the signs right? And unfortunately, I am very, very sure that I have the signs correct here, okay? So the confusion here comes from effectively how we measure or look at time, okay? So if the signal is shifted to the right, then our peak is occurring at a later point in time, and we need our phase angle to be negative to make the math work correctly. If our sinusoid is shifted to the left, then our peak is occurring earlier in time, and our phase angle needs to be positive to make the math correct. So based on this graph right here that I've drawn, I could say, purely by inspection here, that theta must be a negative phase angle, whereas phi must be a positive phase angle, because I would expect my peak value of my cosine function to occur at t is equal to 0, but instead it occurs at what I've indicated as delta t. So that's why I know that theta must be a negative number. And I would expect that my sine function would be 0 and increasing at t is equal to 0, but instead it is it is 0 and increasing at a negative value of time, or before t is equal to 0, and therefore my phase angle phi must be positive in this case. Okay, so I absolutely understand that this shifting to the right gives you a negative phase angle and shifting to the left gives you a positive phase angle may be confusing, but those are the rules. This is how this behaves. Okay, fundamentally, it has to work that way. All right, so how do you all feel about the concept of a sinusoidal waveform in general? I know it's a very odd question, but we do have other things to talk about. So I just want to make sure that we're all kind of on the same page at this point. Does anybody have any questions about the material that we've covered here before I move along? All right. So the next thing that we are going to talk about is comparing sinusoids. And this is something that we're going to be doing quite a bit of. Okay. So when we compare sinusoids, it is common for us to see that they are out of phase, meaning that they have different phase angles. Okay, and we're going to talk about that and the concept of leading and lagging here in a moment. In order for us to accurately even start this comparison, though, 3 very specific criteria must be met. Okay. So our first criterion for comparing sinusoids is that all of our functions must be expressed solely or exclusively as sine waves or cosine waves. We are going to get in the habit of expressing them all as cosine waves. So what I mean by that is, let me do these in colors actually. Let's say that we had a time varying voltage, which I'm going to call VA of t. And this voltage was 8 cosine 5t plus 10 degrees volts. And we had a second time varying voltage, VB of t, that is 5 sine 5t plus 30 degrees volts. In order for us to accurately compare these two waveforms, both have to be expressed as a cosine function or both have to be expressed as a sine function. So this leads us to 2 trig identities that we will use a lot in this class, okay? I'm going to start my list of trig identities way down here because we're going to have like 10 of them. So our first trig identity, number one, is that cosine of, let's call it just x for right now, cosine of x is equal to the sine of x plus 90 degrees. And our second identity is that sine of x is equal to cosine of x minus 90 degrees, okay? So I'm only writing down these two trig identities for the moment. We're going to talk about how to apply them here really quickly. I'm realizing now I might not have given myself enough room, but it'll be okay. So effectively, this whole thing right here, 5t plus 30 degrees, is x in our second trig identity. So to convert our sine function into a cosine function would look like 5 cosine 5t. Thank you, Devarier. I was muted. My apologies. Okay, so what I had said up to that point was that I believe before I got cut off or dropped from, goodness gracious, can't even talk today. So we've been having internet issues here in Methkin Hall. I believe this is the 7th time today that Zoom has dropped me. So if I get kicked off of Zoom again, we're finished for the day, and I'll just pick up wherever we left off. So let's start with that. I believe before I got kicked off of Zoom that I had finished converting the expression 5 sine 5t plus 30 degrees volts into 5 cosine 5t minus 60 degrees volts by applying trig identity number 2. Okay. Now what we are doing is introducing a second criterion for comparing sinusoids. And that second criterion is that all functions must be expressed with positive amplitudes. And now I am making up a waveform VC of t that has a negative amplitude. And we are going to introduce 2 new trig identities to get rid of negative amplitudes or convert them into positive amplitudes. But thank you very much for letting me know that I was muted, or I would have talked for a solid 10-15 minutes before I noticed. So, all right, so VC of t is going to be negative 10 cosine 5t plus 100 degrees volts. And to correct this, or to make the amplitude negative, we're going to introduce 2 more trig identities. So numbers 3 and 4 will be that negative cosine of x is the same thing as positive cosine of x plus or minus 180 degrees. And similarly, negative sine of x will be positive sine of x plus or minus 180 degrees. So effectively, adding or subtracting 180 degrees from a phase angle is the same thing as multiplying by a factor of -1. Our third and final criterion for comparing sinusoids is that all functions must have the same frequency. This could be linear frequency f or angular frequency omega. If they all have the same linear frequency, then they all also have the same angular frequency, okay? So the three different waveforms that I've listed here, VA, VB, and VC, all have an angular frequency of 5 radians per second. So I could compare these. There is no trig identity that exists that will allow me to convert a sinusoidal function with a frequency of one thing to a sinusoidal function with a different frequency, or at least I can't express it as a single sinusoid, okay? So before we wrap things up today by talking about the concept of leading and lagging, I'm going to give you guys the other several trig identities that we need to have in our pocket in order to successfully manipulate these guys, okay? So we're not actually going to use numbers 5 through 9 until class tomorrow, or excuse me, Monday, because today is Thursday, but I'm going to go ahead and give them to you now. So the first identity, this new identity that we're going to have here is sine of x plus y is equal to sine x cosine y plus cosine x sine y. Sixth identity will be cosine x plus y is equal to cosine x cosine y minus sine x sine y. Our seventh identity is sine x minus y is equal to sine x cosine y minus cosine x sine y. And then we have cosine x minus y will be cosine x cosine y plus sine x sine y. And these 5 trig identities you should have learned in your high school trigonometry class. I probably went over them in your pre-calculus classes as well when you talked about trig identities. This next one you may not be familiar with, okay? It is a very important one. In fact, if I were to ever get a tattoo, I would likely get a tattoo of this trig identity. This identity is cosine of x plus j sine of x is equal to e to the jx. Okay. This guy is Euler's identity. And it might look a bit wild and crazy right now. But this single trig identity right here is what is going to allow us to turn a whole bunch of calculus that is going to be very difficult into a whole bunch of algebra that is going to be very easy. This trig identity is the foundation of analyzing electrical circuits in the frequency domain. Okay, so I said a moment ago that I was going to talk about leading and lagging. I'm not going to talk about that today. I just realized I've talked for an hour and 20 minutes straight, give or take. So that's probably about enough of me that you guys can stand. So we're going to cover the concept of leading and lagging first thing on our next class meeting, and then we're going to get into actual steady state sinusoidal analysis. So I hope you guys have a great weekend. If you have any questions about anything or want me to hang around and talk you through performing complex number operations on your calculator, I'm happy to do it, but I'm done lecturing for now. So yeah, have a great weekend if you don't have any questions.